Mathematics is a field which is rife with definitions. If you're studying algebra, for example, it will be important to know the definition of a linear equation. As well, it will be important to understand the definition of a polynomial and a quadratic expression. As you go on in math, you'll learn the definition of continuity, and as time passes, you'll learn even more abstract and rigorous definitions of this concept. In a field as dense with definitions as mathematics, it's natural that one might ask if it's possible to define mathematics itself. So many of us in our youths spend many hours worrying and stressing about mathematics, and a lot of us spend a lot of time in our adulthood worrying and stressing and enjoying ourselves about mathematics. But what the heck is this thing? Well, that's a question I saw posed on today's frontier of intellectual discourse, which is Reddit. And there were a lot of interesting answers to this question. Today, I'd like to talk to you about some of the answers from that Reddit thread, as well as some of the answers to this question historically from mathematicians. Of course, an appropriate dash of mathematics will be thrown in to further enlighten these definitions, and I encourage you to go in the comments and let me know which definition you thought was best or worst, or give your own definition. I'd be really interested to see what you come up with. Tony, the original poster of that thread I mentioned, took a swing himself at giving a definition of mathematics. He said, "Mathematics is the study of producing logical implications through defined, simpler, abstract notions." I think the first half of this definition is alright, but I think near the end where we get that triple combo of adjectives, defined, simpler, abstract notions, that just feels a little clunky. I think we could do better. I'm not sure what purpose any of these three words are supposed to serve exactly. I mean, the word defined, for example, we should suppose that any word that we're using in our definition could itself be defined in a satisfactory way, so I'm not sure why the word defined would need to be here. And then also simpler than what? Are we saying that the abstract notions are simpler than the logical implications? I'm not really sure what that means, and the word simpler itself is perhaps fairly subjective in what it would mean in any mathematical context. The word abstract, don't really have a big problem with that, but going back to the beginning of the definition, I'm not so sure to say that it's the study of producing logical implications is as accurate as we might like. The study of producing logical implications would to me seem like a much more meta sort of mathematics than mathematics itself. There is producing logical implications through proofs, but then the study of that sounds like proof theory, which is one very particular part of mathematics. But it's an interesting first try. Let's move on to the next definition. This is from Alex Kruckman on Stack Exchange. He says, "Mathematics is the domain of inquiry, where logical reasoning is the sole methodology. That is, a question is a mathematical question if and only if it can, in principle, be settled by logical reasoning alone." I'm not sure how I feel about mathematics being defined to have logical reasoning as its sole methodology. I think in practice, the usage of the word mathematics would perhaps not be accurate in places where we would like it to be if this is how we took it. For example, if someone is justifying a result or coming to understand a theorem through some intuitionistic means that perhaps aren't purely logical, but just feel true and make sense, has that person done any mathematics? Have they learned any mathematics? Even if the conclusions they make are true, but their process wasn't solely or perhaps entirely through logical reasoning? For example, if I show that I can take one dot, 1 being the first odd number, and then add the next odd number, being 3, I get a square. And then if I add the next odd number of dots, being 5, I get another square. And then if I add the next odd number, 7, of dots, I would get another square. I may then very confidently feel in my mind's eye that I could continue this, and that in general, a sum of consecutive odd numbers starting with 1 is going to be some square number. But is that mathematics if I haven't employed solely logical reasoning? I should think that it is mathematics, because, for example, example, any proof that happens to contain an error must then contain something that is not solely logical. It contains some logical error. But I would say that an attempt at a mathematical proof should not be defined out of being mathematics. Its author has still done mathematics, even if he has erred in the process. The latter part of the definition, that a question is a mathematical one, if and only if it can be settled by logical reasoning alone, may also bring to mind Gödel's incompleteness theorems. Each mathematical field, at its most rigorous, is founded on a set of axioms, things which are assumed to be true. Gödel's incompleteness theorems, in short, showed that any sufficiently sophisticated system of axioms will contain some facts which are true, but are not provable in that system. Thus, a question or a fact in a particular system could certainly be a mathematical one, but in fact not capable of being solved through logical reasoning within that system. For example, set theory is commonly taken to be the foundation of mathematics, and it's certainly a mathematical question whether or not our common theory of sets is in fact consistent. If in a particular system of set theory it was possible to prove something's both true and false, that would not be a consistent system, but Gödel's theorems showed that it is not possible to prove the consistency of our axiomatic theory of sets within that theory. And hence, if the system is consistent, we will never know. We'll just have to hope. If it is inconsistent, then it's possible a paradox will be discovered eventually. However, this is certainly an example of a mathematical question which we may say cannot be settled by logical reasoning alone. If you look up mathematics in a normal dictionary, you might not be surprised to find a definition that is fairly number-centric, focusing on the quantity and arithmetic part of mathematics. I don't have a normal dictionary on hand to show you, but I do have something better, being a mathematics dictionary. Really, where could one hope to find a better definition of mathematics than in a dictionary of mathematics? So let's flip to the mathematics section of the dictionary and see what it has to say. Something very useless I found when looking up the definition of math on Google was the definition mathematics. That's what math means. That is not very useful at all. But let's see what we can find in this superior, sophisticated man's dictionary. Here is the word mathematics. Let me zoom in for you. Mathematics, it says, is the logical study of shape, arrangement, and quantity. So it in fact puts the number quantity part of math all the way at the end of the definition. I think that's a solid attempt. This definition also uses that term logical, which we've seen, although it doesn't necessarily emphasize that the study need be solely logical. Mathematics is at its heart a great combination of artfulness, guesswork, intuitionistic feel and exploration, and in the end you hope you end up with some purely logical results. It also goes on to define applied mathematics, which is not something I have any interest in, and then there is pure mathematics, the study and development of the principles of mathematics as such, for their own sake and possible future usefulness, rather than for their immediate usefulness. Back on the Reddit thread, somebody mentioned a previous instance of this question where somebody gave an answer with a naughty word in it. So that is my warning to you. Let's look at this definition, which is also more like a joke, really. Math is like a game where you try to say the craziest shit without lying. Like we said, at its most rigorous, mathematics is built upon some set of axioms which are assumed to be true. Those could be viewed as the rules of a game, and from there you're trying to find the most non-obvious, hence craziest, things that you can that are in fact true and perhaps took a whole lot of work to get there. Once we agree on the axioms and definitions at play in a mathematical system, there are indeed many opportunities to find things that are counterintuitive and quite charming. For example, here's a conversation that never happened but which I imagined in my head between a mathematician and some other dude, and they're talking about open and closed sets. Some sets are open. Some sets are closed. Interesting. So every set is either open or closed? Oh no, some sets are neither open nor closed. What? That's ridiculous. Well, surely a set can only be one of the two. So either it isn't open and it isn't closed, or... Oh no. Some sets are both open and closed. What? Yeah, they're called clopen. That's dumb.
It is what it is.
So, for example, if you don't know about open and closed sets, let me give you a quick demonstration. Here's a cute little number line, and let's say that right here is 0 and right here is 1. There's something called an open interval, and we notate it like this: a parenthesis, 0, comma, 1 with another parenthesis. This so-called open interval between 0 and 1 contains all numbers that are both greater than 0 and less than 1. So it doesn't contain 0, it doesn't contain 1, but it does contain all the numbers between them. So it would look like that little segment there with holes at the end because it doesn't contain 0, it doesn't contain 1. The reason this interval is what we call open is that, in short, we could take any number from this interval and there would still be some space around it, which is entirely contained in the interval. For example, if you were trying to prove that this is not the case, you might give me a number that's really close to 0, one of the endpoints, like 0.001, for example. And I might say, yeah, that's a pretty teensy number, but consider the open interval from 0.001 minus 0.0005 to 0.001 plus 0.0005. So here you've given me some number in the interval, and I've given you this space around the number, which is still entirely contained in the interval. This number is not negative, and this number is not greater than 1, so this whole thing is in the interval, and that's the gist of why it's called open. Now, if we take the complement of an open set, or what is in this case an open interval, we will get what's called a closed set. The complement just consists of everything that's not in the set. So the complement of this open interval from 0 to 1 would be the set that contains all numbers down to negative infinity up to 0, which is included, and then we union that with, so throw it in with all numbers from 1 up to positive infinity. This is a closed set, and for an example that contrasts with the openness of this interval, if you gave me the number 0, I could say, well, that is in this closed set, but there's no space around it that is contained in the set. If I try to make any space around 0, that's going to contain some positive numbers that are less than 1, and this does not contain any positive numbers that are less than 1. You can see how it stops at 0 and then skips right over to 1. This feature of this closed set, having a number that doesn't have space around it contained in the set, is not a necessary feature of a closed set, but it is certainly a hallmark feature of some closed sets. For example, the set of real numbers, which we write like this just contains all numbers on the number line, this is an open set, because you could take any real number, and certainly there is space around it that is entirely contained within the real numbers. However, it is also closed, because the complement of the real numbers, the set containing everything that's not in the reals, is just the empty set. If we're only considering real numbers, then the complement of the reals contains nothing at all, and this is actually an open set as well. So since the complement of the reals is open, the reals are in fact closed. While the real numbers are both open and closed, perhaps a quirkier example is the set of rational numbers. These are the numbers that can be written as fractions, and they are neither open nor closed. The set of rational numbers is not open because if you take any rational number, any space around it is necessarily going to contain some irrationals, and thus that space doesn't belong completely to the rationals, so it's not open. However, the complement of the rationals is not open for basically the same reason. The complement is a set of irrationals, and it has the same issue with not being open. Since the complement of the rationals is not open, it's also not closed. So the crazy shit we're saying here, which is very characteristic of mathematics, is that some sets are open, some sets are closed. Some sets are both open and closed, and we call those clopen. Other sets are neither open nor closed, and I don't know what we call those, but let's move on. This next definition also functions a little bit more like a joke. The user EJ Fate said he once heard a mathematician describe a mathematician as someone who says A, means B, and writes C. Unfortunately, the mathematician who said this was EJ Fate's professor, and his professor was right. This funny description of what a mathematician is also gets at the heart of some of what we'll see in some other definitions. That is, the fact that in mathematics, many different things may be given the same name. As a very simple example, if you're in an introductory proofs class, you may hear your professor say that some number n is not even. If he says n is not even, well, what he means is that n is odd. But then it may be that what he writes is n equals 2k plus 1 for some k that is an element of the integers. And certainly when people are learning this stuff for the first time, to say this, mean this, and write this is an easy way to get people confused. Another funny answer given by Daddy Cool, notice how I've artfully written my L here so it's clear that it's not a 1. He said, "Lemma now, dilemma later." He could mean a couple things by this. A lemma, generally, is a smaller, more basic result that is proven in anticipation of using it to prove some bigger theorem. One thing he may mean by this is, we'll prove the lemma now. That's a smaller, basic, more easy result, and we'll worry about the bigger problem that we're really interested in later, and that's the actual dilemma. He could also mean, oh, if we had some lemma, we'd be able to prove this theorem, so let's just assume the lemma now, and it's going to become a dilemma later when we actually have to prove that key fact that our whole entire theorem relies upon. As a really quick example, if we consider 10 divided by 3, I may ask, how many times does 3 go into 10? Well, 3 goes into 10 3 times, so I could say that 10 is equal to 3 times 3 plus a remainder of 1. This remainder is key to a very important thing in mathematics and some applied fields called modular congruence, but the whole idea only works if this is always possible. How do I know that given two integers a and b, where b is not equal to 0, I'll always be able to write a as b times something plus some unique remainder? Well, this very important fact is called Euclid's division lemma, so it's a darn good thing that he proved it. This next definition was given by Bertrand Russell, which was published in the Hilbert Journal in 1914. As you can see, it's a little bit longer than some of the other definitions. And here's what it says. Pure mathematics consists entirely of assertions to the effect that such and such a proposition is true of anything, then such and such another proposition is true of that thing. It is essential not to discuss whether the first proposition is really true, and not to mention what the anything is, of which it is supposed to be true, skip some words to get to the conclusion. Thus, mathematics may be defined as the subject in which we never know what we are talking about, nor whether what we are saying is true. The conclusion of this definition perhaps flies in the face of how a lot of people view mathematics, although I think it is funny and true in its own way. Mathematics being defined as a subject in which we never know what we're talking about, nor whether what we are saying is true. Well, what the heck does Bertrand Russell mean by this? Well, you can see a very easy example of what he means by referring back to set theory, which is founded, when treated most rigorously, on a set of axioms. The most common set of axioms for set theory today are the ZFC axioms. The ZFC set theory axioms do not define what a set is, and so in using them to develop set theory, we do not have any idea what we are talking about. But then again, they're also axioms. There's no way to know that they are true. They are, by their very nature, assumed to be true. So in fact, we would also not know whether what we are saying is true or not, for its truth only follows if we assume the axioms are true. Are the axioms true? We don't know. Hell, we don't even know if the system is consistent. Of course, in practice, as useful as mathematics is, this may seem like a very erroneous definition. This can't possibly be the definition of that super useful thing we call mathematics, but it certainly does have a hint of truth in it, and it's pretty funny. In this next quote, Henri Poincare has given a definition of mathematics in an early 1900s interview. Keep in mind, this would have been done in French, so this is a translation. You can see that it is much shorter than the Bertrand Russell quote. This quote was given in response to a question about what gives mathematicians a feelings of elegance in a problem or its solution. Poincare says, "It is the harmony of the different parts, their symmetry, and their happy adjustment. It is, in a word, all that introduces order, all that gives them unity, that enables us to obtain a clear comprehension of the whole as well as of the parts. Elegance may result from the feeling of surprise caused by the unlooked-for occurrence of objects not habitually associated. In this, again, it is fruitful, since it discloses thus relations that were until then unrecognized. Mathematics is the art of giving the same names to different things. And this, I would say, is my favorite definition, and is usually my go-to when asked about a definition of mathematics, or when the situation calls for me to invoke such a thing. These two users on that Reddit thread gave an answer in a similar spirit, that mathematics is the study of isomorphisms and non-isomorphisms. An isomorphism, in short, is a recognition of some sort of equivalence between two mathematical objects. Sorry that this instance of the word is squeezed a little bit, but it is in fact isomorphic to this instance of the word. To say that mathematics is the art of giving the same names to different things could in part be talking about things like isomorphisms, where some sort of equivalence between objects that are different is recognized, and thus they could in some sense be given the same name. On the other hand, this also describes the abstraction common to mathematical study, where two objects may be different, but there may be some important property they share. For example, the numbers 7 and 9 are different, and if you don't believe me, just ask 6. But even though they're different, they are both odd. On the other hand, the numbers 3 and 5 are different. We may call them odd, but we may also say that they're both prime. We thus, in recognizing important properties, are able to give the same names to different things. Another example that's easy to grasp is the idea of a graph. A graph is a set of vertices and edges that join distinct pairs of vertices. For example, here is a graph that I may call G. It has 4 vertices, and it has some edges that join pairs of these vertices. This may be a graph created to model friendships between people. So maybe we have 4 people, and there's an edge between any 2 people that are friends. On the other hand, I may have some other graph H, which is modeling towns and the different pathways to get between them. Well, in some sense, these graphs are different. They were made to model different things, and they certainly look different. We can observe that structurally they are certainly the same. In that sense, they are isomorphic. The graph G consists of what we call a triangle, with this one edge and vertex connected to the triangle, and the graph H consists of the exact same thing. In graph theory, we would write that G is isomorphic to H. That is an equal sign with an inquisitive eyebrow. Yet another user on that thread by the name of Aaron Gentry says that mathematics is what mathematicians do, and that's perhaps a you know it when you see it kind of definition. Is it possible to describe mathematics? Probably not in a way that everybody's going to be satisfied with, but is there any need in the first place? Is there any controversy about what is and is not mathematics? And really, in that way, mathematics is a lot like love. You know it when you're in it, and when you're not... Why did I bring this up?
From my fate, twisting to escape this. Cutting out my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tone of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really in it.